Welcome. Today we'll explore the fascinating world of quadratic functions and learn how to graph them step by step. Understanding quadratic functions is essential for success in mathematics and many real-world applications. A quadratic function is a polynomial function of degree 2. This means the highest power of the variable is 2, which creates the characteristic curved shape we'll explore. Every quadratic function can be written in the general form, f of x equals ax squared plus bx plus c, where a, b, and c are real numbers, and importantly, a cannot equal 0. Quadratic functions appear everywhere in science and engineering. They model projectile motion in physics, help optimize structures in engineering, analyze profit in economics, and create smooth curves in computer graphics. We'll take a systematic approach to mastering quadratic functions. First, we'll understand their parabolic shape, then identify key features like the vertex and intercepts, learn reliable graphing methods, and finally apply these skills to solve real-world problems. Quadratic functions create a distinctive U-shaped curve called a parabola. This elegant shape appears naturally in many phenomena and has unique mathematical properties that we'll explore throughout this series. By the end of this comprehensive guide, you'll confidently graph any quadratic function and understand how to identify all of its important features. Let's begin this mathematical journey together. The x-intercepts of a quadratic function are the points where the parabola crosses the x-axis. These special points are also called roots or zeros of the function. Here we have a parabola. Notice how it crosses the x-axis at two distinct points. At these points, the y value equals 0. These crossing points are our x-intercepts. In this example, they occur at x equals 1 and x equals 3, giving us the points 1, 0 and 3, 0. To find x-intercepts algebraically, we set y equal to 0 and solve the resulting equation. There are three main methods we can use. Method 1 is factoring. We start with our quadratic function, set it equal to 0, then factor the expression into two binomials. Using the zero product property, we set each factor equal to 0 and solve for x. This gives us our x-intercepts at x equals 1 and x equals 3. Method 2 uses the quadratic formula. For any quadratic equation in the form ax squared plus bx plus c equals 0, we can find the x-intercepts using this formula. Using our same example, we identify a equals 1, b equals -4, and c equals 3, then substitute these values into the formula. The third method is completing the square, which involves rewriting the quadratic in perfect square form. While effective, it's often more complex than the previous two methods. Remember these key points. X-intercepts are where the parabola crosses the x-axis and y equals 0. They're also called roots or zeros. You can find them using factoring, the quadratic formula, or completing the square. Depending on the discriminant, a parabola can have 0, 1, or 2 x-intercepts. Understanding the domain and range of quadratic functions is essential for analyzing their behavior. Let's explore these concepts using the coordinate plane. The domain of a quadratic function represents all possible input values, or x values. For any quadratic function, the domain is always all real numbers from -infinity to +infinity. Now let's examine the range, which depends on the vertex and direction of the parabola. For a parabola that opens upward, the vertex represents the minimum point. The range starts at the y-coordinate of the vertex and extends to +infinity. Now, let's examine a parabola that opens downward to see how the range changes. For a parabola that opens downward, the vertex represents the maximum point. The range extends from -infinity up to the y-coordinate of the vertex. Let's summarize the key concepts about domain and range for quadratic functions. Remember, the domain of any quadratic function is all real numbers. The range depends on the vertex's y-coordinate and whether the parabola opens upward or downward. This understanding is crucial for analyzing quadratic functions completely. Quadratic functions can be written in two important forms, each with distinct advantages for different mathematical tasks. The general form of a quadratic function is f of x equals ax squared plus bx plus c, where a, b, and c are real number coefficients and a cannot equal 0. In general form, the coefficient a determines the direction and width of the parabola, b affects the position of the axis of symmetry, and c represents the y-intercept. For example, the function f of x equals 2x squared minus 8x plus 6 is written in general form. Now let's examine the standard form, also known as vertex form. The standard form, or vertex form, is written as f of x equals a times the quantity x minus h squared plus k, where a, h, and k are real numbers. The key advantage of vertex form is that it directly reveals the vertex coordinates. The vertex is located at the point h, k. The parameter a still controls direction and width, while h represents the horizontal shift from the origin, and k represents the vertical shift. The same function from our earlier example can be rewritten in vertex form as f of x equals 2 times the quantity x minus 2 squared minus 2. From this vertex form, we can immediately identify that the vertex is at the point 2, negative 2. Let's compare both forms side by side to see their key differences. Both forms represent the same quadratic function, but each has specific advantages depending on what information you need. The key takeaway is that vertex form makes graphing easier because you can immediately identify the vertex, while general form is useful for quickly finding the y-intercept and working with standard algebraic operations. The first step in graphing any quadratic function is determining the direction the parabola opens. This fundamental property is controlled entirely by the coefficient a in our general form. The coefficient a is the key. This single number determines whether our parabola will open upward like a smile or downward like a frown. Here's the simple rule. When a is positive, the parabola opens upward. When a is negative, the parabola opens downward. Let's see this in action. First, we'll examine parabolas with positive a values. Notice how they all open upward, forming a U shape. Now let's examine parabolas with negative a values. These open downward, creating an inverted U shape or arch. Let's compare them directly. On the left, we have a parabola with positive a opening upward. On the right, we have a parabola with negative a opening downward. This direction of opening is crucial because it tells us immediately whether the parabola has a minimum point at the bottom or a maximum point at the top. This first step sets the foundation for all subsequent graphing steps. Step 2 in graphing quadratic functions is finding the axis of symmetry. This is a crucial step that will help us locate the vertex and create a perfectly symmetrical parabola. The axis of symmetry is found using the formula x equals negative b divided by 2a. This formula gives us the x-coordinate where the vertical line of symmetry passes through the parabola. Let's work through a concrete example to see how this formula works in practice. Consider the quadratic function f of x equals 2x squared minus 8x plus 6. First, we identify the coefficients. A equals 2, b equals negative 8, and c equals 6. Now we substitute these values into our formula. X equals negative b divided by 2a becomes x equals negative 8 divided by 2 times 2, which simplifies to x equals 8 divided by 4, giving us x equals 2. The axis of symmetry for our parabola is the vertical line x equals 2. Let me show you what this looks like on the coordinate plane. Here is the axis of symmetry drawn as a vertical dashed line at x equals 2. This line will pass through the vertex of our parabola and divide it into two perfectly symmetrical halves. When we eventually draw the complete parabola, you'll see how this axis of symmetry creates perfect mirror symmetry. Every point on one side of the line has a corresponding point at the same distance on the other side. The axis of symmetry is essential for graphing because it gives us the x-coordinate of the vertex and ensures our parabola is drawn correctly. In the next step, we'll use this information to find the exact coordinates of the vertex. Now that we have found the axis of symmetry, we can determine the vertex of our parabola. The vertex is the turning point of the quadratic function and represents either the minimum or maximum value. Let's work with our example function f of x equals x squared minus 4x plus 3. From the previous step, we determined that the axis of symmetry is x equals 2. Here we can see the axis of symmetry as a vertical dashed line at x equals 2 on our coordinate plane. To find the vertex, we substitute the x value of the axis of symmetry into our original function. Let's substitute x equals 2 into f of x. We substitute 2 for every x in our function. F of 2 equals 2 squared minus 4 times 2 plus 3. Now we calculate step by step. 2 squared equals 4, 4 times 2 equals 8. So we have 4 minus 8 plus 3. Simplifying 4 minus 8 plus 3 equals negative 1. Therefore, f of 2 equals negative 1. This gives us our vertex coordinates, 2, negative 1. The vertex is located at the point where x equals 2 and y equals negative 1. The key takeaway is that the vertex coordinates h, k are found by using h as the x value from the axis of symmetry and k as the corresponding y value when we substitute h into the function. This vertex represents the turning point of our parabola. With the vertex identified, we now have a crucial reference point for graphing our quadratic function. This point will help us accurately plot the parabola in the subsequent steps. Now we reach step 5 in graphing quadratic functions, finding the symmetric point. This step helps us identify another key point on our parabola by using the property of symmetry. Let's work with our example function f of x equals x squared minus 4x plus 3. First, we'll draw the parabola and identify the key elements we've found in previous steps. We already know the y-intercept is at the point 0, 3, where the parabola crosses the y-axis. We also determined that the axis of symmetry is the vertical line x equals 2. The symmetric point is the reflection of the y-intercept across the axis of symmetry. Since parabolas are perfectly symmetric, this point will have the same y-coordinate as the y-intercept, but will be located on the opposite side of the axis of symmetry. Here's how we calculate the symmetric point. The y-intercept is at 0, 3. The axis of symmetry is at x equals 2. The distance from the y-intercept to the axis of symmetry is 2 minus 0, which equals 2 units. To find the symmetric point, we move the same distance on the opposite side of the axis of symmetry. So we go 2 units to the right of x equals 2, giving us x equals 4. The y-coordinate remains the same, so our symmetric point is 4, 3. Notice how both points are equidistant from the axis of symmetry. This symmetric point gives us another accurate point on our parabola, helping us draw a more precise graph. The key takeaway is that for any point on one side of the axis of symmetry, there exists a symmetric point on the other side. This property is fundamental to understanding parabolas and helps us graph them accurately with fewer calculations. When graphing quadratic functions, creating a table of values provides a systematic approach to plotting accurate points. This method is particularly valuable when you need multiple reference points to draw a precise parabola. Let's demonstrate this method using the quadratic function f of x equals x squared minus 4x plus 3. We'll create a comprehensive table of values to graph this parabola accurately. First, we choose strategic x values. For this quadratic, we'll select x values from 0 to 4, which will give us points on both sides of the vertex and help us see the parabola's shape clearly. Now we calculate the corresponding y values by substituting each x value into our function. Let's work through each calculation step by step. Now we have our complete table of coordinate pairs. Let's set up our coordinate plane and plot these points to visualize our quadratic function. We plot each coordinate pair from our table, starting with 0, 3, then 1, 0, 2, negative 1, 3, 0, and finally 4, 3. Notice how these points begin to reveal the characteristic U-shape of a parabola. Finally, we connect these plotted points with a smooth curve to complete our parabola. The table of values method ensures we have sufficient points to draw an accurate representation of the quadratic function. The table of values method is especially useful when you need high precision or when working with complex quadratic functions. By choosing appropriate x values and calculating their corresponding y values systematically, you can create accurate graphs of any quadratic function. Modern technology provides powerful tools for visualizing and exploring quadratic functions. Graphing calculators and specialized software can enhance your understanding and help verify your analytical work. Graphing calculators are essential tools for mathematics students. They can instantly graph quadratic functions, allowing you to visualize the parabola and explore its key features without manual plotting. Modern graphing calculators offer numerous capabilities for working with quadratic functions. They can automatically find vertices, calculate intercepts, and allow you to trace along the curve to examine specific points. Mathematical software like GeoGebra provides even more powerful capabilities for exploring quadratic functions. These programs offer interactive environments where you can manipulate parameters and see immediate visual feedback. Software tools excel at providing interactive exploration capabilities. You can dynamically change parameters in the quadratic equation and watch the parabola transform in real time, helping you understand how each coefficient affects the graph's shape and position. Technology integration offers three primary benefits when working with quadratic functions. First, it allows you to verify your analytical work by providing immediate visual confirmation of your calculations. Second, technology deepens your understanding by allowing you to experiment with different parameters and observe their effects on the graph in real time, building intuitive knowledge about quadratic behavior. Finally, technology enables you to explore more complex quadratic functions that would be difficult to graph by hand, expanding your mathematical horizons and problem-solving capabilities. Remember that technology is a powerful complement to, not a replacement for, understanding the underlying mathematical concepts. Use these tools to enhance your learning and verify your analytical skills. Quadratic functions are powerful tools for solving optimization problems in the real world. These problems involve finding the best possible outcome, such as maximizing profit or minimizing cost. Let's examine a profit maximization problem. A company sells widgets, and their profit function is p of x equals negative 2x squared plus 40x minus 50, where x represents the number of widgets sold in hundreds. Since the coefficient of x squared is negative 2, this parabola opens downward, which means it has a maximum point at its vertex. This vertex represents the optimal number of widgets to sell for maximum profit. To find the vertex, we use the formula x equals negative b over 2a. With a equals negative 2 and b equals 40, we get x equals negative 40 divided by 2 times negative 2, which equals 10. The vertex is at the point 10, 150, meaning maximum profit of $150,000 occurs when selling 1,000 widgets, or 1,000 widgets total. Now let's look at a cost minimization problem. A manufacturing company's cost function is c of x equals 3x squared minus 24x plus 60, where x represents production level in thousands of units. Since the coefficient of x squared is positive 3, this parabola opens upward, which means it has a minimum point at its vertex. This vertex represents the optimal production level for minimum cost. Using the vertex formula again, x equals negative b over 2a. With a equals 3 and b equals negative 24, we get x equals negative 24 divided by 2 times 3, which equals 4. The vertex is at the point 412, meaning minimum cost of $12,000 occurs when producing 4,000 units. This is the most cost-effective production level. The key insight is that the vertex of a quadratic function always represents the optimal solution in optimization problems. When the parabola opens downward, the vertex gives the maximum value. When it opens upward, the vertex gives the minimum value. When graphing quadratic functions, students often make several common mistakes that can lead to incorrect graphs and solutions. Understanding these pitfalls will help you avoid them and improve your accuracy. The first common mistake involves the direction of the parabola opening. Students often forget that when the coefficient a is negative, the parabola opens downward, not upward. Here we have f of x equals negative 2x squared plus 4x plus 1. Since the coefficient of x squared is negative 2, the parabola must open downward. The second common mistake occurs when finding the vertex. Students often confuse the formula for the axis of symmetry or make arithmetic errors in the calculation. For f of x equals x squared minus 6x plus 8, the axis of symmetry is x equals negative b over 2a. Here a equals 1 and b equals negative 6. Students often forget to apply the negative sign correctly, writing negative 6 over 2 instead of negative 6 over 2. Remember that negative b means the opposite of b. The third common mistake involves plotting points incorrectly. Students may calculate points correctly, but plot them in the wrong locations on the coordinate plane. For example, if you calculate that when x equals 2, y equals 3, make sure to move 2 units right and 3 units up from the origin, not the other way around. To avoid these mistakes, always double-check your work. Verify the sign of the leading coefficient. Carefully apply the vertex formula and plot points systematically by moving horizontally first, then vertically. Remember, accuracy in graphing quadratic functions comes from careful attention to detail and systematic checking of your work at each step. Throughout this comprehensive series, we have explored the complete process of graphing quadratic functions and identifying their key features. You now have all the tools needed to tackle any quadratic function with confidence. Let's review the essential steps for graphing any quadratic function. First, determine the direction of opening by checking the sign of coefficient a. Second, find the vertex using the axis of symmetry formula. Third, calculate both y-intercept and x-intercepts. Finally, plot these key points and draw a smooth parabola connecting them. Here are the key takeaways to remember. Every quadratic function creates a parabola when graphed. The vertex is always the most critical point to identify first. Use the parabola's natural symmetry to find additional points efficiently. Most importantly, regular practice with different forms of quadratic functions will build your confidence and skill. With consistent practice and application of these techniques, you will master the art of graphing quadratic functions. Remember, mathematics is a skill that improves with dedication and regular practice. Thank you for joining us on this mathematical journey, and best of luck with your continued studies.